All right, then I'm going to hand over the presentation to Kate Stanley from IBM, who will do today's talk on streaming and with structure. I'm going to let you do the introduction of yourself and your talk. So
thank you very much.
Please share the screen if you would like to.
Yep, let me share. Okay, so thank you very much for having me. I've presented at quite a few Jfokus events, but I'm very excited to be presenting today. And thank you very much, Helena and Matthias, for inviting me. So I'm a software engineer. I work at IBM on a product called IBM Event Streams, which is a fully supported Kafka offering. So I'm very engaged in the Kafka community. And today I'm going to talk to you about streaming with structure. I really wanted to start my talk with this slide. Let's get some lunch. But unfortunately, I don't have a lunch demo. I have a coffee demo. So let's get some coffee. So there are plenty of simple getting started demos out there that show where you can start introducing things like Kafka. And one such demo is this coffee shop demo written by Clément Escoffier. You can go check out all of the code on GitHub. But this is a very simple coffee demo. It has some coffee lovers who want to come and get coffee, and you have a HTTP API for them to request their orders at the coffee shop. And then the coffee shop communicates using HTTP to the barista. And you can run this version of this application using the code in GitHub. But if you start to hit it with a lot of orders and have lots of coffee lovers coming into the coffee shop, you quickly find that it's not the quickest or most responsive application, and you get a lot of blocking in the coffee shop because it's having to call out to the barista and wait for the barista to do something and respond before it can go back to the coffee lovers and say their order has been placed. So one of the first things people start to do is say, well, actually, I want to create some sort of decoupling between my coffee shop and my barista. I want my barista to be able to act a bit more independently and get through the orders how they can, but have the coffee shop still giving a nice responsive experience for the coffee lovers. So a way to do this is to introduce event-driven architecture. So we have microservices that are publishing into the event-driven messaging backbone, and then others that are consuming those messages and maybe publishing new ones. And if we add this into our coffee demo, then we have our event backbone between the coffee shop and the barista. And again, this version of the application is available in GitHub for you to run. But basically, we run essentially something like Kafka as our event backbone. And the coffee shop can then post new events into the event backbone to say, I've got this order and this order. And then this leaves the barista more decoupled from the coffee shop, and they can process all of these events as and when they're ready. And if you run the two examples next to each other, you do find if you run with lots of coffee lovers, once you put the event backbone in, you get a much more efficient system, and it's a much better experience for our coffee lovers. And as I mentioned, a lot of people are sort of looking at this and starting to add event backbones, and they're adding things like Kafka. So for those of you who haven't seen about Kafka, I think I did a talk at Jfokus already introing Kafka, but as a reminder, it's an open source distributed streaming platform. It provides stream history, so that makes it a little bit different from some other messaging systems you might have already seen. And it uses immutable data, so these events are immutable events coming in. And Kafka is really focused on being highly available, scalable, and providing very scalable consumption. So that's where the stream history comes in as well. You can have a lot of consumers reading from the topic, reading all the events, but also from different points in the stream history. So if you add in things like Kafka, you go look at all of these demos, it's really easy to think, okay, if I add Kafka in, everything is going to be decoupled and it's going to be great. But unfortunately, that is not the whole story. So let's look at why just adding Kafka doesn't immediately give you decoupling, and what you can do to help solve that and add structure to your streams. So all of the data in Kafka is actually stored in bytes. They don't have different formats for you to store your data depending on what you're doing. Everything that comes in and out of Kafka should be a set of bytes. So this means when you're producing and you're consuming, the producers and the consumers have to format the data before it goes in and then when it comes out again. So the way they do this is probably familiar to many Java developers. We use something called a serializer and a deserializer. And there are default serializers and deserializers that come along with Kafka. So we have the string serializer here and the integer serializer. So if we just use the standard default serializers that Kafka provides, what does that mean for our coffee shop demo? So here we have the coffee shop is the producer and the barista is the consumer. If the coffee shop wants to create some sort of event, we need to think about what format that's going to take. So if we're going to use a string serializer, we might just have a string event that looks like this. We have an ID, a product, a customer, and a size. So if we convert this to what an actual order would be like, we might have something like this. So we have 1, 2, 3, 4 is the order ID. We're ordering hot chocolate because no matter how much I talk about coffee demos, I actually don't drink coffee, I drink hot chocolate. And we have the order name, which is Kate, and size small. So if I send this through to the barista, as long as they understand that this is the format the event is going to take, then they can create all the orders and everything is fine. But this doesn't give us room to evolve our events over time and evolve our coffee shop. So what happens if we decide, actually, we want to offer people who order hot chocolate to add marshmallows as an option? If I send a new event through that has this marshmallows true set in it, then in the best case scenario, the barista will ignore this unknown field and maybe I'll get my hot chocolate but without the marshmallows. But in the worst case scenario, it leaves the barista wondering, what do I even do with this order? And I might not even get a hot chocolate. And it's actually worse than that because the coffee shop has a lot of different format types that it can choose from. So if you use XML or JSON, and if they change their mind and decide later, actually, I want to produce this event in a different format, how on earth is the barista going to know which format to use? So we need to think about how can we add structure to our messages and how do we make sure that the coffee shop and the barista are always talking the same language? So the first way to start looking at structure is to think about, okay, I need to pick something that's better than just a string. And an obvious first choice is to go for JSON. So JSON is a format that many people are familiar with. Most languages now have good support for JSON. So that seems like a good starting point. So I can get structure quite happily from JSON. I've now got an order ID, a product, customer, a size. I can reorder these fields and the consuming application will still understand what's going on. And a lot of JSON parsing libraries do have a capability where they can easily ignore unknown fields. So if I add marshmallows true and my application doesn't understand marshmallows yet, I probably won't fail. But the thing that you don't get from JSON is you don't get any additional metadata. So there's nothing to stop the coffee shop saying, well, we do still offer marshmallows, but we've decided instead of putting true or false, we're going to put yes or no as a string. And at this point, my barista would still be confused about whether or not they should provide marshmallows. So although we can get some additional structure from using things like JSON, this isn't actually good enough to bring us enough structure that our barista and our coffee shop are always talking the same language. So this is where a schema comes in. A schema is like a blueprint for your event. It provides the structure and the different types that you should have in that particular event. And actually, this is very similar to the Open API documentation that a lot of people are already using with your HTTP APIs. If you're writing a REST-based API, you should always make sure to provide a version and a documentation so that people know how to interact with it. And you should do the exact same thing for your events. So if you've provided this schema, you now need to think about how you make that schema available to both the producer and the consumer. So the simplest and first option you can look at is just providing the producer the schema and the consumer the schema, and they each have their own copy and they communicate like this. This will work fine for a while, but if you decide to update the schema and change your message, you need to work out how to communicate that to the consumer so that they understand this new message. So one way to look at doing that is just saying, well, what if I send the schema with the message? So if I've got a JSON object, which is my event, I could just add a schema in there. I can provide the properties that are required. So here I've provided an order ID and said that's of type string. The size is a Boolean, which doesn't make sense, but there we are. So we can have a schema inside our message, and that again will work okay. But if you put a schema inside every single message you send into Kafka, you're going to quickly find that every single message you send into Kafka has a whole extra set that's just not needed. Because ideally, you're not going to change the schema every time you put in a new coffee order. You're just going to change it when something changes about your system. So really, we want a way that makes sure the consumer knows which schema to use, but they're not having to pass the schema in every single message that goes through Kafka and slowing down your throughput and using up more resources. So this is where a schema registry comes in. So a schema registry is just a centralized store for all of your schemas, and your producers and consumers can then talk to the schema registry to get the schema that they need and correctly process the messages. So once we have a schema and a schema registry, we can start to imagine that our producers and consumers can be talking the same language and understand the messages that are always going through. But there are two outstanding questions that we have to answer. One is, what format of schema are we going to use? And the second one is, how do we actually know which schema in that schema registry the consumer should use to process the message? So let's first look at schema formats. There are plenty of schema formats out there, so I'm not going to give you a list of all of them, but the three most common that seem to be used with Kafka at least are JSON schema, Google Protocol Buffer, and Apache Avro. So JSON schema is a vocabulary that allows you to annotate and validate JSON documents. So you can see an example here of a snippet of what a schema would look like, provides things like the type and the different properties. You can say, for example, that size is a string and it's an enum of small or medium. You can say that there's specific fields that are always required. And the nice thing about JSON schema is, because the schema is written in JSON, it's very readable for both a human and a machine, and it helps you to describe your existing data formats. So it's designed for describing JSON objects. So feel free to check out this project. And JSON schema is a good place to start if you're just looking at existing JSON events and want to describe those. The second one that I've seen people use most is protobuf. So that's a mechanism for serializing structured data. It's created by Google. It's language neutral. It supports a lot of different languages, and you generate code to interact with it. So I've seen this being used a lot when people have applications that are in lots of different languages and want to have the same across everything. So you provide a .proto file. So you do have to learn how to write a .proto file, but it's not too bad. You can see here we've got an order which represents our schema, and you can say certain fields are required and what type they are. And then because I can generate code in whatever language I'm using, I can then interact with it in a very sort of familiar way for that language. So the Java example here, I can create an order from a new builder. I can set the order ID, the product, whether it's got marshmallows. So it's pretty familiar to use. But it does mean you have to do this code generation and have generated objects before you can start interacting with them and writing your code. The final one, which is actually the one that I've seen the most people use with Kafka, is Apache Avro. So Apache Avro is a data serialization system that provides very rich data structures. It has a compact, fast binary data format. So that fits well with Kafka in terms of converting into a binary format. And it has very simple integration with dynamic languages. So with Avro, you can do code generation, but you can also do it without code generation. So I'll show you that in a sec. So for Avro, you provide all of your schemas actually in a JSON object format, but inside a file, which is a .avsc file. So you can see here we've got our particular file. We have to give a type, a name, and the fields. So my type is record, the name is the name of my schema, and then the different fields for my actual schema. So then you can provide, similarly to the others, the type. So here I can say product is of type string, but you can also have very nice different sets of types. So you've got the enum at the bottom like we had in the JSON schema, but you can also provide something called a logical type. So I've put UUID here, but actually the logical type I've seen most people use is dates and times. So that's a really nice way to add even more metadata for your consuming applications to understand exactly what they're looking at. So when you actually use an Avro schema, you can use it without generated code. So here you can see that I'm using the generic data object in Java, and I can create a record. So I do generic data dot record, and I can put in the different objects. And this is really nice, I find, particularly if you're just starting out, because you can prototype things and get going with Avro really quickly. And then once you're happy and you're sort of wanting to move on, then you can look at generating code later on down the line as well. So here we have all of our different format options, but how do we actually choose which schema we should get from the schema registry? So first for that, we need to think about how do we identify a schema? And this actually varies depending on which schema registry you're using. So some schema registries will store an individual schema, a specific version, as a separate artifact. So here I have ID1 and ID2 of the same schema, but they're just different versions of my order schema. And I might have a schema registry that stores them separately, and they each have their own unique ID. But there are some schema registries that store one specific schema and then multiple versions within that. So that's what I have on the right-hand side. I have, again, my order schema, and the order schema is referred to with the ID1, but it has separate versions within that. So in that case, to specifically identify one schema at one particular version, I have to provide both the ID and the version. The schema registry that use these types of storings will often allow you to provide just the ID and it will pick the latest version. But if you want a specific version, you might have to provide two different IDs to uniquely identify it. So you do need to have some understanding of how your schema registry works. But once you understand that, you can then look at, okay, how do we make sure the consumer knows which schema to use without having to send the schema along like we showed earlier? And for this, we do need to understand a little bit about Kafka records. So in Kafka, all of the events are stored as records, and they're made up of a key and value pair. The key is optional, and if you provide a key, Kafka uses it for some kind of routing of where it goes within the topic. But the core information here is that you can provide schemas for both the key and the value, but the value is the bulk of your content. So if you were providing things like your order and the size of it, the customer name, that sort of thing, they'd normally go in the value, and the key is more like a unique identifier. So if I had a customer ID, that could go in the key. So the first way that we can send all of the schema IDs that we need across is using something called magic bytes. So if we imagine this is a set of bytes that represents the value of a particular record, if it's been produced by an application that is using schemas and is using the magic byte mechanism, then this set of bytes can be separated into three parts. So the first part is called a magic byte. This is an indicator to the consumer to say, this value here has a schema ID as part of it. It's not just a pure value by itself. The second part is then the integer schema ID. So this is the unique global ID that identifies specifically the schema that was used to produce this message. Then finally, we have the serialized data, which obviously the consumer needs to then read. So if you're using magic bytes, you could have a scenario where both the key and the value have a magic byte in them and the same or different schema IDs to identify the schema used for those different parts. So the good thing about this mechanism is all of the information that you need for your schema ID is included inside the record that gets sent as part of Kafka. It's all contained in there, and we're not sending the whole schema anymore. We're just sending that one ID, which leaves the consumer room to go and get the schema if they haven't got it in their cache already and read the message using the schema. The downside of this is it pollutes your messages. So now if you're passing through Kafka, you know that every single message you send has this extra bit on the front. And in Kafka, there is a special setup of a topic you can use where you would want to send null values sometimes. And if you've got to send a schema ID on the front, then this starts to get a little bit tricky. So there is a slightly cleaner way to do it, and that's using record headers. So in Kafka, we have the key and the value, which makes up our record, but in 0.11.0, they actually added something called record headers. So this is a sort of scenario that is actually fairly similar to other messaging systems. A lot of other messaging systems have this idea of a header, and it represents additional metadata that goes through with your event. So in Kafka, it's really easy to add new headers to your messages. So you can see some Java code here where I'm creating a producer record, and I can just do .headers.add, add my header, and you can add multiple different headers. So here you can see I'm putting in a header that says, this is the ID, and this is the version that I want you to use for my schema. So then the consuming application can read the headers, get the schema ID out, go fetch the schema, and then process the message. So the nice thing about this approach is you're not polluting your key and value anymore. It's in separate information in the headers, and if you've got applications that are wanting to sort of introspect things as they're coming through, it can be a lot easier for them to just pick the headers out than having to actually process the value. But what this means is we have two different approaches. One with the magic bytes where the schema ID is included in the key or the value, or both, and one where it's included in a record header. And a lot of schema registries actually support both. Partially, this is because the magic byte option was the only option when we didn't have record headers in Kafka. So a lot of schema registries added this option first, and then when record headers came in, they added the record header option because people preferred that. So you can do either, but the important thing is that your producer and consumer have to agree on which one they're choosing. Because if your producer puts a magic byte in and puts the schema ID in the key and the value, but then your consumer is looking in your record header, then they won't match up. And I see a lot of people running into problems where their consumer is saying unknown magic byte. And that's normally because they're looking for a magic byte in the key or the value, and it's just not there because the producer put it in the header instead. So you need to think about which option you're going to choose, which suits your use case, but make sure that you line them up so that you're talking the same language. So finally, in terms of how we integrate with Kafka, we need to think about, okay, we've got our schema ID, we know, are we going to do magic bytes or headers? We've got our format and our schema registry. How do we even utilize this as part of our Kafka flow? So in Kafka, there are three sort of broad types of applications you can write. There are producers and consumers, which are the standard Kafka clients that most people start off with. There is Kafka Connect, where you have connectors that other people have written that are designed to pull from an external system into Kafka or out again. And there are Kafka Streams apps. So Kafka Streams is a Java library, and you can write an application that does stream processing using the nice features that Kafka Streams provides. Confusingly, all of these different types of application have different mechanisms for you to configure how to use your schemas. So I already introduced the producer-consumer one at the beginning. Producers and consumers configure their serializing and deserializing using serializers and deserializers. These are the config options you have to provide in your app. So key.serializer, value.serializer, key deserializer, value deserializer. So when you've picked your schema registry, what you need to do is find the class that provides a serializer for that schema registry, for that format, and for the specific configuration option you've chosen in terms of magic bytes and headers. And then you provide that class to your Kafka app in the configuration. And what it will do is it will automatically use that class to serialize the data before it goes to Kafka, or if it's a consumer, to deserialize it before it comes into your actual logic that you've written. So for producers and consumers, you configure a serializer. For Kafka Connect, you configure what's called a converter. So under the covers, this is still doing serializing and deserializing, but for Kafka Connect, you don't have to provide a separate serializer, deserializer. You provide one class, which is called a converter. There are some default ones that are provided, so JSON converter, string converter, byte array converter, And these match up to the sort of default string serializer deserializers. But if you're using a schema registry and schemas, you need to go and find the converter for your schema registry and configure that as part of Kafka Connect. So the final one is Kafka Streams. Again, Kafka Streams uses something different. They use SERDs, so it's just short for serializer deserializer. So you have to provide the key.serd and value.serd. Again, there are some default ones if you're just using the default serializers and deserializers, but if you're using a schema registry, then you'll need to find the SERDs for your schema registry that knows how to get the schema and knows how to convert from the format that you've chosen. With Kafka Streams, it's worth noting that you can provide a default and then override it within the stream. So if you want to pull from a topic that you're using one type and then push to a different topic with a slightly different type, then you can do that at a sort of code level. But you do need to go find the right classes to use. But what this means is if I have a system like this, where I have an external system and I'm going through Kafka Connect, using a Kafka connector to get into Kafka, and then I'm using a Kafka Streams app to do some processing, maybe creating a new topic, and then I'm consuming from there, I need to make sure that my converter, SERDs, and deserializer all line up. So if my converter is using record headers for the schema ID, then the SERDs needs to also use record headers so that it can get the schema ID information out. And if their converter is using Avro, then it makes sense for the SERDs to use Avro. So they're all using the same schema registry and they're all looking for the ID in the same way. This is the thing I get the most questions about when people come and ask me questions about schema registries in Kafka. They've picked their schema registry, they've picked their format, but they haven't picked the right classes for the different types of application and the flow doesn't fit together. So now I've talked about schema registries, the different options and why you might want one. I'm just going to talk quickly about Apicuria Registry. So this is an open source schema registry. It provides multiple format options, including Avro, Google Protocol buffers, and JSON schema, and it provides multiple storage options as well. So you can store your schemas in Kafka using Kafka Streams, or you can use something like a database or Postgres. The nice thing about Apicuria Registry is it does actually support lots of different types of schemas. So it very easily supports the common ones that are used with Kafka, but if you want to use it to store schemas for your sort of REST-based APIs or things like that, then you can do that as well. They also provide IBM and Confluent compatibility APIs. So the classes that I talked about earlier, the serializer, converter, the SERDs, all of those are written and understand how to talk to the specific schema registry that they're written for. So if they're Confluent ones, they're for the Confluent schema registry. If they're the IBM Event Streams one, they're for the IBM Event Streams schema registry. Now, Apicuria Registry supports all of those. So you can use the serializers from Confluent or from IBM to talk to Apicuria Registry instead if you want to. So actually, in the product that I work on, we've recently moved across to adopt Apicuria Registry as our core schema registry because it provides so many options for different people to use. So if you're already looking at existing demos and things like that that are using one of these other libraries, then you could probably still use it with Apicuria Registry. And if you're looking at Avro, which is the one that a lot of people start off with Kafka, then these are the different classes you can use that are specific to Apicuria Registry. So they provide a serializer, deserializer, a converter, and a SERD. But as I mentioned, you can also use the IBM and Confluent ones with it as well. So in summary, you should definitely use schemas to get structure into your events. It's important to make sure that your producers and consumers are talking the same language so that you don't end up with additional coupling between those applications that you weren't expecting. So you can use a schema registry to provide you as a centralized store, and there are so many options in terms of format and identification mechanism, but it's worth doing a little bit of research, understanding what you're doing so that your applications don't run into errors down the line. If you are interested in a fully supported Kafka offering, then feel free to check out Event Streams. As I said, this is the product that I work on. And with that, I have a whole set of links for you to get started. So if you want to read more about sort of general intro to schemas, we have some of those on our Event Streams docs. I've listed a whole set of links for Apicurio, including a demo if you want to try that out. And I've also linked some stuff for getting started with Kafka. So there's a quick start guide, which is just you running shell scripts, really easy, takes like 5-10 minutes. Strimzy is a Kubernetes operator for Kafka, it's open source. And then if you want to try a Vertex-based app, then I have one. This is the app that I talked about at Jfokus this year with Grace. So that is all I had in terms of slides. So thank you very much for listening, and I will welcome any of your questions.
That's great, Kate. Thank you.